Hello everyone, this is Group 3. Today we are going to show you how to solve question 12 from tutorial 4. Before we start with the solution, why don't we tell you a bit about our equipment. Our group was assigned to solve question related to pipes and ducts. So, what is the function of pipes and ducts? They are used to transfer fluid from one point to another, simply that. As for everyday application, we see it everywhere. For example, our house piping and air ducts in the ceiling. Now, let's take a look at the questions. Steam enters a long horizontal pipe with an inlet diameter of 16 cm at 2 MPa and 300 degrees Celsius with a velocity of 2.5 meter per second. The exit conditions are 1.8 MPa and 250 degrees Celsius, and the diameter is 14 cm. Now, determine the rate of heat transfer in kJ per second. After reading and understanding the question, the first thing we should do is to lay out an imagery of the question. We draw a schematic diagram of the pipe. From the question, we know that the inlet and the outlet of the pipe are of different diameters. Therefore, when we draw the diagram, it should look like this. Then, start listing down given information on the diagram. Based on the equation, we know that the inlet conditions are P1 equals to 2 MPa and T1 equals to 300 degrees Celsius. And the outlet conditions are P2 equals to 1.8 MPa and T2 equals to 250 degrees Celsius. Now we got that done. Let's start listing down our assumption. First assumption, it is a steady flow process. This is because the total amount of mass contained within the pipe does not change with time. The second assumption, the kinetic and potential energy changes are negligible. There is no height difference between the outlet and the inlet of the pipe. Thus, delta Z equals to 0. Whereas for kinetic energy, if we were to calculate the change in kinetic energy, it's very small. The value is very close to 0, thus it is negligible as well. The third assumption, there's no work interaction and no heat gain. In the pipe, there's no device such as turbine or heater connected to it. Thus, there's no work done on the system or done by the system. After listing down our assumption, the next thing we should do is to construct the energy balance equation, which is E in minus E out equals to delta E. In the previous chapter, we have learned that E is equals to U plus KE plus PE. However, the following equation is only true for non-flowing fluid. For flowing fluid, there's another energy involved called flow energy, and it is a product of pressure and specific volume. So now we have E equals to flow energy plus internal energy plus kinetic and potential energy. And previously we have also learned that enthalpy is equals to internal energy plus flow energy. When we substitute H into the first equation, we will get E equals to enthalpy plus kinetic energy plus potential energy.
Next, by substituting the total energy equation into the energy balance equation, we will get Q in plus W in minus Q out plus W out equals to change in enthalpy plus change in kinetic energy plus change in potential energy, which Q in, W out, change in kinetic energy and change in potential energy are all equal to 0, whereas for Q out, we can see that there is temperature difference between the inlet and outlet temperature, so this indicates that there is heat loss. With that, we are left with negative Q out equals to change in enthalpy. However, the question asked us to find the rate of heat transfer, which in this case is the rate of heat loss. Thus, our final answer will have to be in the form of joule per second or kilojoule per second. So, the more proper equation would be negative Q out equals to mass flow rate times the change in enthalpy. Which, if we expand the equation, it will be negative Q out equals to mass flow rate times H1 minus H2. To determine the value of H1 and H2, we refer to table A6 as it is stated in the question that the fluid is steam, which is also known as superheated water. From table A6, when pressure is 2 MPa and the temperature is at 300 degrees Celsius, H is equals to 3024.2 kJ per kilogram, and when pressure is at 1.8 MPa and the temperature is at 250 degrees Celsius, H is equals to 2911.7 kJ per kilogram. Now we have the value of H1 and H2, we are left with the value of the mass flow rate. To find the mass flow rate, we can utilize this equation, which mass flow rate equals to volumetric flow rate divided by the volume, where volumetric flow rate equals to volume times the area, and also by the formula of volumetric flow rate equals to volume times pi over 4 times diameter in the power of 2. To find both the volumetric flow rate and the mass flow rate, we utilize the inlet condition. At the inlet, velocity is equals to 2.5 meter per second and the diameter is equals to 0.16 meter. We will get the volumetric flow rate equals to 0.05 meter cube per second. For the specific volume of the steam at the inlet, we refer to table A6 and we will get that specific volume is equivalent to 0.12551 meter cube per kg. Next, substitute all of the values into the mass flow rate equation and we will get that mass flow rate is equals to 0.401 kilogram per second. Now we have all the needed values, we can calculate the rate of heat transfer. And we will get that rate of heat transfer is equals to 45.1 kilojoule per second. Hope our video helped you to understand how to solve the question. See you again next time.